Hello, my name is Mohammed Bahri. I'm a PhD student at Faculty of Science and Technology, CETAT. Today I will present you our research work titled Efficient Control of a Three-Phase Grid-Connected PV System. The plan is as follows. First, we have an introduction, then system configuration, and we'll present the objectives of the control strategy. We will then show the system modeling, the control strategy used, and to demonstrate the performances of this strategy, we will present the simulation results, and finally a conclusion. So, photovoltaic energy is one of renewable energy forms. It permits to produce electricity by converting solar irradiation to electrical energy using photovoltaic cells. Moreover, the photovoltaic systems connected to the grid are the most used due to their advantage than the autonomous system. For that, we have devoted our research to study the system in order to inject a maximum photovoltaic power with a good quality to the grid. As you see, the studied system consists of a PV array coupled to a three-phase grid, three-phase voltage source inverter, and finally through a simple low-pass filter with its resistance R. And there is a three-phase load also connected to the system. The advantage of this configuration is that it doesn't need a DC-DC converter, which decreases the global cost of the system and the number of sensors used. The three-phase load connected to the system will be supplied by the PVG power when it is sufficient, or by the grid when there is no sunlight, and finally, when the PVG power is unable to supply the load, it will be supplied jointly by the PVG power and the grid at the same time. The three-phase load represents a hard source of system perturbation. The main goal of our work is to develop a new control strategy able to realize the following objective. First, the maximum power tracking MPPT. So, achieving a maximum power tracking under every climatic conditions. The second objective is to obtain a unity power factor by compensating the reactive power generated by the load. And the third aim is to apply a control able to compensate the harmonic distortion caused by the load. And the most important point in this work is to develop a control able to realize all the aforementioned objectives in presence of system perturbations. We are speaking here about parameters disturbance of the system and harmonic pollution of the load current. This point has never been treated in any research. If we use a higher switching frequency, the harmonic component will be pushed to the higher frequencies. So, we can filter out the harmonics by using a simple pass filter with a cut frequency near to the fundamental frequency. Now we need to model the system in order to develop an advanced control strategy. In front of us, the electrical scheme of the PVG that contains NP number of modules in parallel. Every module is formed by NS number of photovoltaic cells in series. The choice of NS and NP is linked to the desired values of the voltage VPV and the current IPV. The expression of the photovoltaic current IPV is given by several researchers by the following equations. We remark that it depends on temperature G and solar irradiation G and PVG voltage VP. Now, this is the mathematical modeling of the global system based on electrical equations of different parts of the system, where VA, VB, and VC are the inputs control of the inverter in ABC frame. To simplify the development of the controller, we applied a DQ transformation to convert the previous model into the following model in DQ axis. Here, VD and VQ are the input control of the inverter in DQ axis. Now we will explain the control strategy. The following figures shows the variation of the photovoltaic power in function of the PV voltage under different irradiation and temperature. We remark that the maximum power corresponds to the point where the derivative of PV power with respect to the PV voltage equals to 0, like P1, P2, etc. So the first output chosen is the derivative of PV power with respect to PV voltage that must converge to 0 in order to exploit exactly the maximum power produced by the PVG. To choose the second output, before us the expression of reactive power produced by the inverter, where ED is the direct component in DQ axis of the grid voltage, which is constant. So the reactive power can be controlled to compensate the reactive power caused by the load by controlling the quadratic component in DQ axis of the inverter current to converge to a reference which will be defined after. So then the second output chosen to be controlled is IQ. We see here the tracking errors used to develop the controller for the studied system. The goal is to force the errors to converge to 0 under atmospheric condition changes and system perturbation. For that, we use an advanced technique, which is the backstepping control that is based on Lyapunov stability, which permits to stabilize the system under any conditions and give more flexibility in the level of the control synthesis. After having applied the backstepping technique, we elaborated the control laws VD and VQ, which are used to control the inverter in order to achieve the objectives. And this is the representative schema of the system and the controller. As you see here, the output generated by applying the backstepping method are used by PWM to generate the switching signals of the inverter in order to realize all the aforementioned goals with a good performance. To demonstrate the performance and robustness of this controller, we present here the simulation results. The figure below shows the scenario used in the simulation, where we defined an abrupt variation of temperature and irradiation intensity, as well as disturbance of the input capacitor. Also, the load current shows an harmonic pollution at 2.5 seconds. The following figures shows the references of the inverter output voltage. We remark here that the curves of the reference have a sinusoidal form without distortions and fluctuation, signifying that the PWM outputs will not contain very fast variations. Therefore, these outputs will not saturate the inverter switching and will not lead to unwanted heat generation in the level of the inverter. This figure presents the curve of the first output, which is the derivative of PVG power in function of PVG voltage Vp, which converges to 0 with a very good precision and very fast response time. The convergence of the first output of its reference implies the achievement of the MPPT under abrupt variation of solar irradiation and temperature and in presence of system disturbance, as shown in this figure. This figure shows that the active power delivered by the inverter is maximized, so the inverter active power tracks the PVG power with a very good precision and fast response time. The active power flow between the inverter, the grid, and the inductive load is presented in this figure. The load can be supplied by the inverter active power, the PVG power, where it's sufficient, or by both the grid and the inverter active power, where the inverter active power isn't sufficient, like the case between 0.5 and 1 second. We remark that the load active power is constant under abrupt variation of climatic conditions, which guarantees a good operation of this load that represents a good advantage of this controller. The following figure shows that IQ converges to its reference IQ-ref defined before under any conditions with very fast response and very good precision. The exact convergence of the output IQ to their references involved the achievement of the UPF, the unity power factor, as described in this figure. Indeed, the UPF is realized in both cases when the grid receives the PVG power and when it feeds the load. This figure shows the achievement of UPF in presence of the input capacitor perturbation and harmonic pollution of the load current. And finally, the following figure presents the grid current harmonic spectrum. We remark that the control strategy proposed allowed the elimination of the harmonic distortion of the grid current. To conclude, in this work we elaborated an advanced control strategy for a three-phase grid-connected photovoltaic system with a boost converter. The controller uses the backstepping technique based on a nonlinear model or of the system in DQ frame. It permits to realize the MPPT and UPF with very high performance, very fast response and good precision. Moreover, the controller shows a good robustness in front of system perturbations that represents the best advantage compared to the other controllers. The simulation results demonstrate the best performance of this strategy. And thank you for your attention.